Okay, so let's look at a logistic growth model. Of course, if you'll remember from a couple videos ago, I'm just going to draw a really crude little graph up here. We had an exponential growth model in which a population grows unchecked and what's called a J curve. This is a J curve, an exponential curve, right? This is the exponential model. And we were able to calculate that. We were able to see that more is being added as time goes on. More individuals are added with each successive generation. Now, what we need to do is consider limiting factors, right? So I'm going to draw a logistic curve now. The logistic curve is going to look more like this, and it's going to level off eventually, right? The reason it levels off is because there's something called K, or carrying capacity, which is the maximum number of organisms that an environment can sustain or can support. If you look back at the previous video, you know that there's limiting factors. Some of this is scarce food supply, predator interaction, things like this. So there are limiting factors, and for almost everything on Earth, there's obviously only so much that an environment can support. This is known as K, so it's a new variable for a formula here. Keep that in mind. If you want to copy this down so you can see these different curves and maybe write these curves down so you can see how they look different, please do. I'm going to erase it for the time being, just so we can start working on the math portion of this problem. Okay, so let's take a peek at this problem. This should look somewhat familiar because I'm using some of the same numbers from the exponential growth problem, and there's a reason for that, which I will expound upon in a bit. A population of 166 squirrels, right? That's what we're starting with. So for n, our starting n, I'm going to put 166. That's the number of squirrels we're starting with. There is a per capita or per individual growth rate of 0.21. I didn't put units on this, but you could put units, individuals, per period of time. It's all that is. Our max per individual. I'm going to put 0.21. 21. Okay. And also, there's something different here. Let's take a look at this. Carrying capacity of 430. You may ask what carrying capacity is. Carrying capacity is the amount of individuals, again, that this environment can support. So, 430, that's our max, right? The environment can't support anymore. Okay, so if you take a look at these formulas, the exponential growth formula, which is right here, exponential, this is exponential growth. This below it here is logistic growth. You see some things that are very similar. You should. dNdt, R max, and these are all the same. The only difference is we have this little modifier out here, which helps to account for the fact that our population can only grow so large. Okay, so I do the chart method. I think some of you should be doing this as well because it's much easier. So let me write dn over dt over here. Dn over dt. And let me put a very crude line coming down. Okay. Next I'm going to put R max. This is our per capita growth rate. Stop that. R max, per capita growth rate. That's going to be the same all the way down. Okay. Next we have n. Okay. Another line over here. And our final factor that we're going to be multiplying stuff by is k minus n over k. This is what's different. This last column right here is what's different from exponential growth. If you take your hand and cover up this k minus n over k, this should look pretty much exactly the same as the last exponential growth problem we did. So let's go ahead and begin right here with some things that we know. We know our population starts at 166 individuals. Big. We're looking for how big it grows after 3 years. This is the same problem as exponential growth. We just want to see how logistic growth is a little bit different. All right, so let's go. 0.21. R max, that's our growth rate. Our per capita or per individual growth rate is 0.21. So normally we would multiply, for exponential growth, we would multiply these two, because that's what the formula says, right? R max times n. We would multiply these two numbers to get our dNdt. That would give us 35, right? And we would add n to dNdt to get our next generation population size. But we can't do that here. I'm going to leave this 35 here. This is for exponential growth. I'm just going to put it in parentheses. That's not correct. That's not what we're going to use. But let's just pretend for now that we can remember this number in our mind because we're going to see how it's different for logistic growth. So K minus N over K. Well, what is our K? K is 430 minus N. N is 166. Let's divide all this by 430. Okay, so if you calculate this out, which I recommend you just put this in decimal form, you should get some sort of decimal between 0 and 1. So go ahead and calculate that out, pause the video, or just hold on because I'm doing it on my phone right now. Let's see here. 30 minus 166 divided by 430. I got 0.61, approximately 0.61. So this is our first K minus N over K. So for logistic growth, we need to multiply R max times N times K minus N over K to get our d and dt. Of course, with exponential growth, it's 35. Let's see what it really is for logistic growth. This is the real number we're going to use over here. All right, go ahead and multiply 0.21 times 166 times 0.61. You should get about 21. 21, right? So what do you notice? Is 21 greater or less than 35? Well, it should be pretty obvious. 21 is less than 35. Logistic growth is slower, even if you're not, 166 is not very close to 130, really. But it's still going to be a lot slower growing than exponential growth. So that's just something to keep in mind. I'm going to go ahead and erase this so we don't get confused here and just put in the 21. Put in the 21. Okay. All right. So dn over dt is 21. All right. So 21 plus 166 is going to give us next year's n. So what is it going to be? 187. That's this number plus this number. It's going to give us our next generation. So our max remains the same. Last thing we need to do is this problem right over here. So 430 minus. Now keep in mind, with each generation, n changes. So your k minus n is also going to change. Minus 187 all over 430. Let's calculate that out. All right, 430 minus 187 divided by 430. It's going to give us around 0.57, somewhere in there. Close enough. All right, so we've got to multiply everything. We've got to multiply R max times N times K minus N over K, and that's going to give us our d and dt over here. Okay, so go ahead and do that. 0.57 times 0.21 times 187 is going to give us about 22. About 22, right? So if we take 22 and we add that to 187, that's going to give us next year's population size. So after 1 year, this is our population size. After 2 years, 187 plus 22 is going to give us, wrong spot, 209, 209 individuals. R max stays the same. K minus N over K, 430 minus 209 over 430 equals, go ahead and calculate that out. Whoops. Calculate that out. I will do it as well. 430 minus 209 is equal to 221 divided by 430. All right, we got 0.51. 0.51 here. So 0.51 times 0.21 times 209 is going to give us around, let's see, 0.51 times 0.21 times 209 gives us around 22 again, something like that. So d over dt is still 22. Okay, so now you can take your n, add your dn over dt. Again, this is after 2 years. We should get our correct number here. 209 plus 22 is going to give us 231. That's n. 231. That's it. Okay, so after 3 years, we should have 231 individuals approximately in our population, assuming all of this is correct, right? Now, if you wanted to continue on, what you notice is that as you go up, this dn over dt number is going to start going down. 21, 20, 15, 10. This dn over dt number is going to start going down because you're approaching, if you'll remember our curve, you're kind of approaching that as you get closer to this, limit. that number that you add each time as you get closer to the carrying capacity, K. As you get closer, the amount you add each year is going to start decreasing and decreasing until you're not really adding any individuals, right? So when I talk about R max and K, I like to also talk about the fact that you have, and these are some terms you might want to write down if you haven't already from a previous video, R selected species and K selected species. K selected species. R selected species, R selected species are reproduce. When they reproduce, they have many children. They don't have a lot of parental care. In other words, R selected species are predicated upon their rate. How fast can they grow? They are typically exponential growers, and then they will have a fast, large drop-off. These are R selected. Now, K selected species tend to be dependent upon this K, or carrying capacity. They tend to have more parental care, less offspring. Humans are a good example of this. Elephants are a good example of K selected species. Good example for R selected species are most insects. Lots of fish are R selected species. So this is just kind of a way to think about species and how they interact with their environment. R selected, K selected. It's a very general usage term, so they're not, there's some that don't fit neatly into either category. But in general, R selected, lots of offspring, low parental care, not a lot of parental care. And K selected species usually have low amounts of offspring with a high level of parental care. Okay, I think that's it for this portion. Thank you for watching the video, and I'll see you next time.